Hi, my name is Adrian Moscoro, and today we're going to discuss lateral spreading of liquefied soils. We're going to answer today why does soil spread, how does it spread, what historical earthquakes have observed lateral spreading, what is affected by lateral spreading, and can lateral spreading be prevented? In order to talk about lateral spreading, we first must define liquefaction. Liquefaction is a monotonic, transient, or repeated disturbance of saturated cohesionless soil under undrained conditions, causing excess pore pressures to increase and effective stresses to decrease. These movements are typically caused by earthquakes. First of all, what types of soils liquefy? Well, typically non-plastic saturated soils such as silt, sands, and gravels that are located below the groundwater table tend to liquefy. You don't have to have groundwater table. You could have perched water, but basically it's due to shallow groundwater. Also, loosely deposited soil, soils that geologically were deposited, like colluvial, alluvial, or fluvial deposits that aren't in dense condition, also have a high potential for liquefaction. And young soil deposits, such as the late Holocene deposits that are anywhere from 0 to 1,000 years old, those two haven't had the time to settle, or the matrix, in the structure of the matrix to settle, and can be more susceptible to liquefaction. There's other factors as well that have to do with liquefaction, such as the size of the particle. The size, such as gravel, if it gets too big, the weight gets so big that you're not going to get movement of the soil, so liquefaction is not going to be possible. The shape has to do a lot with it. If you have a rounded material, a rounded soil, it'll tend to shift a lot easier than angular material. Gradation. If you have a well-graded soil, you don't have a whole lot of pore spaces, and if you do, any of those pore spaces are filled in with smaller soil, and so you don't have a whole lot of shifting going on, which is necessary for liquefaction. Plasticity as well. If you have a plastic soil such as clay, the cohesion in the soil will prevent it from movement, and it will not liquefy. There's two types of liquefaction. One is flow liquefaction, which is the static shear stress is greater than the shear strength of the liquefied soil. And the other is cyclic mobility, in which the static shear stress is less than the shear strength of the liquefied soil. These two conditions occur based on the magnitude of the earthquake and the existing state of the soil and its structure. But when we get cyclic mobility deformations, these are what we call lateral spreading. Lateral spreading is the movement of superficial soil layers or blocks in a direction parallel to the ground surface, which occurs when there is a loss of shear strength in a subsurface layer due to liquefaction. And it typically occurs in very gentle slopes, less than 5%, in cohesionless liquefiable soils in shallow groundwater, as previously explained. Lateral spreading essentially is a separation of the Earth's surface, or the crust. The crust isn't what liquefies. The crust is what rides over the liquefied soil, and is what causes the spreading. And lateral spreading has been reported from anywhere from a few centimeters to a few meters of permanent displacement, and cumulatively more damage has been observed or has been caused by lateral spreading than by any other form of liquefaction-induced failure. Here's a picture of a lateral spreading that occurred near a bank. As you can see, the wide spreads that are possible in lateral spreading. Lateral spreading, as the soil shakes, what it does is it creates or causes the soil to consolidate. And what happens, the bottom of the soil increases in density, and the water that was filling those voids rushes upward. And if the soil's permeability is not sufficient enough to allow that water to dissipate fast enough, you get increased pore water pressures. If the pore water pressure increases above the static strength of the soil, that's when you'll get liquefaction to occur. Lateral spreading affects many things, such as bridges, mainly the abutments and the foundations because they're located below ground. Buildings, the footings in the buildings get affected as well. Lifelines, lifelines can be anything such as pipelines, water lines, roadways, anything that have to do with our everyday well-being. Since they're underground or have, interaction with the ground in a sense, they can be highly affected by lateral spreading. Here's a couple of pictures of some lifelines. On the left we have a picture of a ruptured pipeline and the roadway, which have been significantly distressed due to lateral spreading. And on the right we have a roadway an access roadway that was again significantly damaged. In countries where very few roads are located, destruction such as this one can impact it significantly if that was the only entrance to a certain area or region. With all this spreading that occurs, engineers and seismologists have been trying to figure out, can we determine what the amount of spreading is? What's the potential of spreading? Well, there isn't anything to exactly pinpoint the spreading, but there has been some investigation and observance of existing or previous earthquakes, especially in the western United States, in which Ute and Perkins measured the magnitude of the earthquake and the displacements. And they came up with what we call liquefaction severity index. And that is termed the general maximum D value in inches for lateral spreads generated on wide active floodplains, deltas, or other areas of gently sloping late Holocene fluvial deposits. So we can't accurately depict how much of a spread will occur, but we can get some type of indication if the soil conditions are similar to historical earthquakes. Historical earthquakes that have experienced lateral spreading date back from 1906 San Francisco to most recently 1995 Kobe earthquakes. And all these earthquakes listed here have experienced a tremendous amount of distress due to lateral spreading. Picture on the left shows a picture of the 1906 San Francisco earthquake, and on the right we've got 1964 Nagata earthquakes. Both of these show significant distresses, one to roadways and one to bridges. Picture on the left shows destruction of a railroad line in the 1964 Alaska, and on the right we see destruction near water for the 1995 Kobe earthquake. So can we prevent liquefaction from occurring, and lateral spreading in general? Well, we can't totally eliminate liquefaction and lateral spreading, but we can mitigate it. A few methods of mitigating liquefaction are listed here below. One way is to excavate the liquefiable soil and recompact it. Another is dynamic compaction, in which we impact the soil from the ground surface with a heavy load at a high altitude, and it compacts the soil down deep below. There's vibrocompaction and vibro replacement, which we will talk about shortly as well. And then construction of seawalls. You can have setback distances from these free edges where lateral spreading occurs more often. And then you can design your structures and foundations to allow them to move with the spreading. Well, we're going to discuss vibrocompaction and vibro replacement a little more in detail. Vibrocompaction essentially is a method to help mitigate liquefaction, and vibrocompaction is essentially the densification of liquefiable soils by inserting a high-powered vibrator into the ground. The soil is penetrated until the required depth is achieved, and then vibrations are induced as a vibrator is pulled out. This will result in a lowering of the elevation of the ground surface, but structural fill may be placed to bring the ground surface back to a required grade. Here's another method, vibro replacement. And the vibro replacement method involves inserting, again, high-powered vibrators into the ground, which laterally compact the soil. As the soil is compacted, it is replaced by stones to form stone columns. And these help to mitigate liquefaction in the soil and also help to increase the bearing capacity of the load for the buildings. So today we have, in our discussion of lateral spreading, we discovered that lateral spreading is due to the liquefaction of soils. We found out that cyclic stresses induced in the soil are caused by earthquakes, in which case lead to lateral spreading. We know that lateral spreading from liquefaction is possible only due to the liquefaction of non-cohesive saturated soils. There's also other parameters that can eventually lead to liquefaction, but for basically non-cohesive saturated soils are what liquefies. We learned that damage in liquefied soils can occur above ground, such as building and bridges, but it can affect the below ground aspects of those as well, such as the footings. And roadways above ground and below ground, we have lifelines that can be affected as well. Historical earthquakes, like we said, any earthquake that you've mainly heard about in the past that was significant has probably experienced a lot of lateral spreading. And can we totally mitigate or can we totally eliminate lateral spreading? No, but we have techniques that can help mitigate lateral spreading. And this concludes the video, and hopefully now in the future you can see an earthquake and be able to define and talk about lateral spreading a lot more. Thank you, and have a good day.